All right, Cyber Patriots, this is Daniel, and this is the Cyber GeoU channel. We're going to continue studying our Cisco content by getting into Chapter 7 in Module 3, IP addressing. So IP addresses are critically important to understanding how networks work, even though they can be a little bit on the complex side to understand, especially early on when you get into the subnet masks and binary math and that sort of thing. If you've seen some of this material already, you've already gotten into that. So we're going to compress this quite a bit because, again, we're looking at this from a Cyber Patriot competition standpoint, not so much preparing for a CCNA or some other kind of a network certification exam. So we're going to touch on some of the need-to-knows and how we would handle this from a competition standpoint and defer a lot of the other content, the binary math and some of those calculations and logical ANDing and all that, but we'll defer that for another day. Okay. They start out with one of their kind of, I guess, make it real kind of exercises. So they're going to talk about Internet of Everything, fine activity if you want to get into it, but probably not pertinent for Patriot perspectives. IP4 addresses. So they're going to begin to talk about it some. And if you've seen IP addresses before, you know they're broken up into 4 sections of numbers. And we call each of those, you might have heard us refer to those as octets. And the reason is those numbers in their native form, the way they're used, are actually binary numbers. And so they're showing you an example here. There's a device on the network, this computer, and see there's 4 sets of numbers separated by periods. And this gets into, if you translated this binary into its decimal, you'd see the more familiar form of its decimal number as opposed to this binary. But the binary is important for the subnet masking. Again, we'll allude to some of that. But just to know that there is the binary there, and that you have to go a little bit deeper when you get into certification level exercises. All right, IP4, that's the version of IP addressing that we use right now. I guess they've run out of IP address space because it wasn't managed very well to begin with. Honestly, not sure what happened with IPv5. I think there was one. It didn't take off at all. And so you'll see some talk about IP6. They haven't really gone to that en masse just yet because they've come up with creative ways to extend the life of the IP4 plus the IP6 conversions. A pretty significant undertaking to take the whole internet and all the various network devices and people managing all that stuff and do it. So we're going to focus on the IP4 right now. Everything in Cyber Patriot we've seen has been IPv4, so we'll focus on that. Okay, you got a video here converting between binary and decimal. That's probably one I would do just to get familiar. 8 minutes and 25 seconds. Would do that just to get familiar with it, and then you'll get into some of the positional notation and trying to explain how number systems work. We're so used to 10-based numbering that we're so used to 10-based that you kind of think that's how numbers work, and everything else is some weird variation. But a base 10 system, a base 2 system, base 8 system, whatever, base 16 system, all of which have some implications in computer science. They're all just numbering systems. So it's good to be familiar with that idea, though again, not necessarily getting too deep for Cyber Patriot. More on the conversions. Again, this is some mathematics that it's all fine, but we're going to probably have numbers already set up for us for the exercises we'll be into. So here they are. It's a drill. Just work on converting this binary to a decimal. And they're showing you in the 128 position, there's a 1. That means you use it. You don't use any of these. There is also in the 2. So this is probably a 130. Let's see if I can get it right. Okay, and so that's 130 in decimal. But again, idea is you take whichever one where there's a 1, you use that number in decimal. If there's a 0, you don't. So you use the 128. You don't use any of these. You do use the thing in the 2 position, and you add that. So you can play with that a little bit. Good exercise. And then going the other way, decimal to binary conversion, if you got to reverse it. And they're going to talk about that too. And again, they're just working towards subnetting. And same thing. So here's an exercise where you take the bits and you got to fill in ones and zeros when you had a decimal of 2. This is an easy one because all you need is the 2 position and everything else is a 0. And so we'll do one example just for fun and check it and plot into the right answer. Okay, and then there's a couple of binary games. Again, don't recommend going that deep with it. So now we get a network and host portions, and some of the final result side of this is important. That when you get an IP address, and now they're showing us the binary along with the decimal form. You get an IP address, and they'll show a 192.168.10 dot, and then there's a 10. And when you see these, they're split into part of this is the network and part of this is the host, or I'm overgeneralizing, but that's the computer's part of it. So if you were to think of a network in your house and you've got it set up and your Wi-Fi router, for example, is giving out IP numbers, and if you looked at each phone and your Xbox or PlayStation and any laptops or tablets or what have you, you would probably notice that they all have a different number here in this last portion, but similarities with at least the first two and more than likely the first three. And so what that's telling you is that the network portion means everybody that's on this set of the numbers, they're all on the same network. And then the way we differentiate computers or devices within the network is off this fourth octet, this fourth portion, dot 10. So if this is dot 10, another computer on the same network would have 192.168.10 dot, but then something other than 10, because then they're both using the same number. Same network over here with the 3 octets to the left, but would need to be a distinct number on the right. Now, if you were to happen to see something and it had something other than 192.168.10, if it has 192.168.11 or 12 or some other number here, or even further up in the first 2 octets, then you're talking about something that's on an entirely different network. So they're separating the network portion of the number and the host portion. Now here's where it gets more complex. You don't always just assume it's these first 3 octets of the network and the last portion is the host. That's where some of this binary math stuff gets in, where it could be a situation where the first 2 numbers are the network and then all of these are the hosts. That's a larger network with a lot more possibilities for how many devices you have. And that's kind of what drives this, is how many machines do you think you'll have on the network? Since we've seen that from a binary standpoint, I'll just tell you this part, you can get up to from number 1 up through, and this is the number 9, I think. See, 1, 2. Yeah, that's the number 9 if you convert that to decimal. Sorry, 10 to 8 and 2. So that's the number 10 in decimal. If you filled all ones, if you filled out like how many possible numbers could you get out of these 8 binary numbers, it could go up through 255. And so that means you could have up to, on this network of these 3, up to 255 different IP addresses that were unique. And so when you get to a number of computers on the same network, it's more than 255, and a large office building or a large network could have that, well, then you got to do something different. So then you got to take this dash line, slide it over some, and start borrowing from this part of this number and divide it, and then you can get much, much larger numbers. Every time you go to the left one, you kind of add a power of 2 to what the binary number is. And so sometimes how you base this is just a function of how many computers do you need to have on your network. There's also things that have to do with how your ISP assigns it and so forth. Main idea here is just understanding a portion to the left is the network, a portion to the right is determining same computers on the network, but their IP address that's specific here in this 4th octet, or wherever the slider moves along. And we'll touch on that a little bit more later. Okay, now here, this is straight off of a screenshot from a Windows PC's IP properties. You can see its IP address, 192.168.10.10, so I think that's the same as what we just had. Yeah, okay, so they're using the same number. So that's its number. And so the network part is these first 3, and the subnet mask in this instance is telling you that. So this subnet mask means basically this is the number you use for this whole network, not just this one machine with the IP address of .10. For this whole network, this 255 tells you that, okay, this 255 here, that means that's part of the network. 255 here means the 2nd octet, part of the network. 255 here, 3rd octet, part of the network. A 0 here means, okay, we're not going to say that's the network part. All these numbers are available to be used for IP addresses. And then the gateway is telling you this is the IP address, this specific address, and notice it's on the same network, 192.192.168.168.10.10. Instead of any .10, this one, of course, has to be different on this part. It needs to be the same with the first 3. Its address is .1. And that means that's the router where if this computer is going to talk to another computer, it checks, are you on my network or not? And you can do the math that's here to figure that out. And if you're not on my network, then I've got to figure out how to get that to you. And if you're on another network, that's more complex. So you don't try to go and send that to that computer that's on another network. you send it to this address because that's the router. And routers figure out how to get things to other routers where you can know how to talk to a computer that's elsewhere. So again, that's really brief over a lot of really deep mathematical stuff, but that's the beginnings of how to know what you're seeing when you look at this in your properties. And when we say Default Gateway, notice it talks about local router interface. So that's just telling you that's what your router address is. And when we get into some of the exercises in the Cisco Network Academy, we'll work with that a little bit, doing some routing inside and outside of networks. Now they're going to get into a great concept, logical ANDing, which is how you take the subnet that's here and logically AND it with here and figure out what is on the network and what's not. A little beyond scope, but stuff, if you took the certification test, definitely need to be ready for it. From a Cyber Patriot standpoint, I think we just need the concepts so that we can do the exercises. So they're going to show you doing some, so this is again, the subnet mask. If it's 255, that means all of the, in a binary sense, they're all ones. So they're showing you a subnet mask that goes all the way through here. And notice this subnet mask doesn't have a 0 here. It has a 254. So this is a network that lets you have like two numbers on it. So that would be a really, really small network. Not really viable. Now here's something that's actually practical. Here are different kinds of subnet masks. So if you notice, here's the one that we're used to, 255, 255, 255, 0. We're all ones, all ones, all ones, because this number in binary here is the same as 255 in decimal, and then zeros. So that's the one that's the most common. You sometimes hear that somewhat mislabeled as a Class C address. We'll talk about that too. But you'll see that pretty commonly. You'll hear network people refer to that as a quote /24, because if you counted all the ones, 8 and 8 and 8, well, that means that you went up to 24 spaces here, and then a 25 borrows one here and so forth. So what we're saying is that this is all the network portion, and then this is all, these are all numbers, 255 of them in this case, available to assign to all the devices on your network. Now look at this. You could go as big as to say this part's network and this part's network, but that is a lot of possible devices on your network. Pretty seldom actually need something that large unless some sort of giant corporation or something. And notice 8 plus 8 being used in the network portion. So with 255.0.0 subnet mask, you'll see it's also referred to as a /16. Now the other thing to be aware of that you could run into is notice how now they're actually taking ones and encroaching the network portion into the fourth octet, the last set of numbers. So instead of having 255 numbers available, each time you take one of these, you cut it in half. So now you've got this at a 128. So if you had to do it, that 1 and zeros, that's the binary counterpart to 128 in our decimal numbering system. And it cuts down by half the number of devices mathematically you could assign. So these are becoming increasingly small networks down to where you've only got you can only have like 3 devices on this and like 8 or something on this and so forth. So, but just being aware, you've got these subnets that showing you the decimal, or the binary side of it, and then these references that you'll hear for a /whatever network. In reality, what people do is they learn this stuff enough to pass the certification test. And then if you do this a lot, you end up memorizing some of these things, like what network node gives you, what network subnet mask gives you how many available addresses. And if you do it this often enough, you memorize it. If you deal with it some of the time, but not enough to memorize, you end up going to, you end up doing this. You go to Google and you say online subnet calculator. And you put the stuff in there and let you figure it out. So, all right, so moving on past that bit of subnet. Types of addresses, host, last host, broadcast. So there's some reservations. There's some specific rules about actual specific numbers beyond our scope, I think, to spend time. Network host and broadcast addresses, again, that's not worth 11 minutes. You could look at that if you want, but consider that probably extra credit, so to speak. Using the Windows calculator with network addresses, they're going to have you take numbers and put them in and go between binary and decimal, I think. Can't hurt to familiarize, but probably not CP essential. Another lab converting between that and binary. So they're doing a good thing, get you used to the stuff, get you prepared so that do enough drills and do them from enough points of view that it starts to become familiar, and you could do it if you needed to. So now we're back to assignments on host. And there's two ways to do this. This is an important concept. Notice what they say. Devices can be assigned to an IP address either statically or dynamically. So a static address means that you go into the device and you yourself type in that this device's IP address is going to be 162.168.10.10. And then you would have the subnet mask you would put in and the router address, the default gateway as well. And you can do that if you need to make sure that a certain computer, certain device has a certain IP address. There are situations when you need to do that. But think about this. What if you've got a very large network with lots of devices, and you go in and have to manually configure every IP address on every device, and then you've got to track all that in some sort of a spreadsheet, keeping track of all that stuff, and then you change a device out and you have a PC that goes down, you've got to change it out, you got to go back and look up the spreadsheet. Okay, that computer that died, I think it was .10, so now I use .10 for the new one. That gets unmanageable very quickly in a medium, larger network. So what you have is there is this thing called DHCP, and I don't think they touch on it here, where you can set up a server or a service on one of your servers that hands the IP addresses out. Generally, if like on your Wi-Fi router, you can look at it and it'll even give you the option, what range do you want to pass out? And that's how most of you who look into Wi-Fi routers, you'll be able to see that it's giving out numbers instead of having to manually configure them. So as an example, here's mine. And I have several because I've got the VM going, but the one that matters, wireless LAN adapter Wi-Fi. So that's my wireless network adapter getting an IP address from my Wi-Fi router in the other room, and it gives me 192, almost looks kind of familiar, 192.168.1, and I got number 140. Notice it uses the same subnet mask, the mathematically simplest, the 255.255.2.5.0, and then my default gateway, you almost could figure that one out because it's got to be the same network, 192.168.1, same network, but then traditionally you have the router get the first, get the .1 or whatever, the first available number. Traditionally give that to the default gateway address. You don't have to, but that's just sort of the convention, make it sort of predictable as people are doing things on the network or someone else has to work on a network someone else set up. And so that's .1, that's .140. JD's over here to my left. She's on another laptop. We could check. It would also have the 192.168.1, and it would be something like 139 or 141 or something like that, like every other device in the house. So that's ours right now, and you could do a CMD and do the same thing and check yours. Okay, let's see. All right, now here's dynamic assessment. So, assignment. So notice here it was use the following IP address. So that's when they say static. That means you're going to click that radio button in the network properties of this is from a Windows computer point of view, and you're manually typing this stuff in because you want to track it specifically yourself and configure it yourself. The easy button, if you can, is say obtain an IP address automatically. This stuff gets grayed out because you're letting you send a broadcast message. You basically shout across your network, hey, I'm booting up. I don't have an IP. Can somebody help me? DHCP server comes back. There's a brief network conversation. DHCP server comes back and says, here, you can use this address. And it keeps track of who's using which one. So you don't have to, and make sure two devices don't try to use the same address. That can get messy really quick. And keeps that out of trouble and just handles that overhead for you. So that's default behavior and definitely recommended if available. IP4s, unicast. So let's talk a little bit about that. A unicast address. Notice this machine sent something to the router. It wanted to get that message specifically to on its same network. So what network is it? 172.16.4. They all have the same first 3 octet numbers, but then they all differ in the 4th octet. So here's .1. That's kind of iffy if it's a 255.0 because what's the router's address? .2, .3, and .253. All on the same network, so it hits a switch, and it doesn't need to go out and ask the router, how do I get there, because it's on the same network. So it can just send that message. It just sends it out. Switch says, yeah, that's on our network. Let's just keep it in-house. We can handle it from here. That's when you're sending something specifically, unicast, uni, one, a specific message to a specific node or other computer, other device on the network. within the subnet, within that network. Okay, unicast transmission. So we're going to show this one. It's going from .1 to .253. Again, it's sending this message straight out from one device to another. I'm going to get to the, okay, here's a broadcast. This is different. This is where one device wants to talk to all the devices, but all the devices within its own network. So it's going to hit the switch. You're going to see, I think, it go from 4.1 here, and you'll see it go to all of them, including up to the router. But a broadcast, usually you don't want to send broadcasts off to everything on every other network that this router might have. So it'll get to the router that says, no, I don't think so, unless it's been configured to do so, which would be away from best practice and become a bad idea very quickly for network traffic. But it says, hey, I need to tell everybody. And it shows these 3 devices, but if there are 100 within this network that's connected to the switch, then I'll have that same set of first 3 numbers. If there are 100, they would all get it. Broadcast means tell everybody in the room. So it's like shouting something to everyone in the room at once, but something that's where someone's in another room, another building, you've got to have another means for that to get that message to get to those other intended recipients. Okay, a multicast. So a multicast is kind of the in-between, I guess you might say. And it's going to a selected set of hosts. So this wants to get to some of these that have the this 224 network, but not the ones that aren't. So that was its intent, was I don't need to send it to you guys, but I do want to send it to these. So multicast hits specific multiple recipients. Okay, then they're going to give you an exercise. Recommend this one. They'll do a little demo. They'll click start. It'll show something happening. It counts down your time. You get 10 seconds, and then you click on which one of the devices are going to get it. If it's a unicast or a multicast or a broadcast. That one's a good exercise. I would do a few of those. More packet tracer utilities. We'll get more to packet tracer later. Public and private. Again, this is important. You end up in a way memorizing this as much as you do getting any mathematics of it. But they ran into a problem years ago that they mismanaged how they gave out all of the IP numbers, and they ran out. I mean, they just mathematically ran out of numbers. Too many devices on too many networks. And as they gave ISPs all of these numbers, eventually ISPs ran out of being able to hand them off. So a way to buy some time was they came up with a specific set of numbers that are used on internal networks, but they don't go out onto the internet. And what that means is that I can use the number 192.168.88.1. No, let's use the right one. 192.168.1.140. So I can use this IP address, this network with this 140 IP on my network, but you might find if you did an IP config, just if you go to command prompt type IP config, you could find that you have the same network and maybe even the same IP address used on your network, because your network is private to you, mine here is private to me. And so you can basically reuse addresses as long as they're private or away from the rest of all the internet. And then you don't have that uniqueness requirement except within the network. That bought them a lot of time, and that's pretty much how things are rolling now. There's some IPsec out there to deal with the numbers problem, but going to private IP addressing. So let's talk about when and how you do that. What they did was they took 3 very specific sets of IP network ranges, and they said these are private, and you can't use them on the internet, even if you wanted to. Anytime you see a 10 in the first octet, that is a private number. If you tried to take your public web server and give it a 10 number, it wouldn't work. But you can use that as a private number, and that gives you, notice it's a 10, so it's a /8 or a 255.000 subnet. And you could get a lot of numbers if you use .10. 192.168.0.0, so notice that's /24. So any numbers with these two numbers in the first octet, like what I'm doing, for example, that is a private number also. And you can use those internally, all you need. And then the 172.16 numbers, another set of private numbers. So that's a way that they bought some time by saying, here, take all those numbers, you use those all you want to behind your router, behind your network, where they won't conflict with identical numbers on someone else's network. And then for all the numbers that are out here in the internet, where the internet does route them around, you don't use these, and that's where the problems are, where each number does have to be unique amongst each other. Okay, and so the big thing is that I would think is if they threw this at us in Cyber Patriot, knowing these numbers being these particular prefixes 10, 172.16, and 192.168, but those are the private numbers, and others could be our legitimate public site numbers. Okay, pass or block, so that's whether or not it's a private or a public. I'll probably mess one up, but okay, if I say start, so what they do is start, that's a 10 number, I'm going to block that, and I didn't do it in time. 145 past that, it says +1. So what it'll do is you just got to know the numbers, and if they are ones that are okay to be passed on the internet, meaning they're not one of those three ranges, you pass it. If it is one of those three ranges, then you block it, but you got to do it before it gets there. And honestly, I have a little trouble seeing it in time to be able to calculate and do it. So, but I think after you get to 10 total correct, it lets you pass on the exercise. Okay, special addresses. There's the loop back address, which is 127.0.0.1. That's you. But it's always when, if you don't know your IP address, you can ping that and it'll be pinging yourself, regardless of what IP address you've been assigned. So that's the loop back. It's kind of a way to kind of check. It's basically just a troubleshooting piece that they put out there. Then there is, now they're going to get into the legacy class addressing, the class A, class B, class C. That's where they screwed up badly in how they assigned numbers to begin with, until they got into, okay, this is doing class full. There's a thing on class full IP addressing, as opposed to class less, which means we don't say that certain numbers are class A because there's just the first 255 octet, or class B where it's the first two numbers are 255, or class C is where it's all three. So they said, let's stop doing that because we're throwing away addresses by the handful. And so they went to classless and or CIDR, I think the acronym, they use the CIDR acronym in here somewhere. Good to just understand the concept of it, but again, not excruciating detail. Assignment of IP addresses, so somebody has to decide who gets which one of these numbers. And you have a thing called IANA that handles it, and then they have this deal where they're showing you globally what regions are assigned to track and hand off the IP addresses that do need to be assigned out to ISPs. Okay, now we're going to take a public or a private and drag each one. So just as example, you take the 10. All right, remember 10 is one of our ones that has to be private. I'm going to drag it over here, and you can do all these, and then I'm going to do a check, and so it says that's okay. If I take 10, and if that were over here and I did that, did a check, it's going to say, no, that's wrong. So remember, the incorrect, that part means just you haven't done all of them, but you can tell right here if you want to check these one at a time or, do the whole thing. So good exercise. Identifying IP4, optional, definitely there, just for time's sake. Now going to IP6, and that's just where instead of the 4 octets of numbers that we have, they've gone to something else, and we'll get to where we could look at one. They're different. Okay, so they're a mess. 1, 2, 3, 4, 5, 6, 7, 8 blocks of 4 numbers. So they're much larger. They're a whole different deal to try to memorize. So there's some complexity with IPv6. I have personally never studied it much. I've never been in an environment where I had to go to it because the private addressing has held off the problems with the public, so, or with the lack of numbers left to assign. So good just to know there is IPv6, and it's going to look very differently. So you see this, okay, that's an IPv6 number. Still not quite the adoption. People thought IP4 would have died probably years ago, but they're managing to squeak by on it, and I think people want to because the 6 is more complex to manage. So you've got some of this stuff, and of course that's a whole different deal than 192.168.1.10. So it's even getting into hex stuff with doing some of the hexes, the A through F on using those as numbers. And so more IP6 stuff. I would recommend maybe read the first slide or two just for context, and then I would skip the rest. And IPv6 covers 724 for a while. And so as we get into dynamically assigning, which is a good thing if you ever have to deal with it, then IPv6 multicasting. Okay, now out of the IP6. ICMP, which is traditionally, you'll just hear that called ping. That's just basically saying across the network, hey, are you there? And so I'm going to say, can I reach this one? And he sends a ping, and he sends it with this machine's name or IP, and it sends that echo, and it says, yes, I'm here, and it sends that back across the network, says, yeah, it's there. You get into that a lot on your network when like you're just trying to check, one, is a device up and running, and is there a clear network path? Because if this had not worked, there's two different things that could be going wrong. One is it's saying, are you reachable? And this one says no, and because this machine is down. If it's down, it's not going to get the request and reply back with the echo. The other thing could be, and often this is what you're troubleshooting for, something's wrong with one of the network devices that it's not passing this correctly. You've got something from a network path standpoint that's jacked up. So what that does is let you test end to end, is this stuff working? Is traffic able to pass through? So it could be both the device on the other end, but not necessarily. Could be traffic in the middle. Extra caution you got to watch though. It's becoming more and more common as a security measure on your routers and your switches to not allow ping. So you would say, is ping reachable? And it would get dropped by one of these network devices before the host device or the recipient you're looking for was able to reply, because the devices, as a security measure, don't allow pings to get through. So it's not that this machine's down or that something's misconfigured. In fact, it's by the network engineer's design that ping traffic isn't going through. And the problem is there's ways to take pings and do some techniques with pings or phony replies to pings and actually cause problems on another network. Like if you're trying to DOS somebody, you get a bunch of devices and you send pings and make it look like someone else's echo. And so everybody, you pinged it, and then you spoofed where you pinged from. And so so you would say something like, if you want to DOS it, like let's say you've got 192.168.30.1, and let's say this is 30.2 down here that's on the same network, and you're a hacker and you don't like these guys, you would send the ping to this machine, but instead of it showing your actual IP address, you spoof the packets when you send them, and this is the recipient, and then you do it over and over and over. And so this machine sees a ping and gets a reply saying, okay, yes, I'll reply, but he thinks it's this one. And then you do that en masse, and you create problems on their network, and you DOS that network. So a lot of times, just to prevent some of that kind of stuff and some other related attacks, network admins will disallow that. But good thing to understand, and when we get into the exercises, we will use the ping to do end-to-end checks to make sure that we've got things configured and devices are working like they should. IPv6 router solicitation and advertisement messages. We will skip the 6 stuff. More ping stuff, checking the local stack. So that's pinging 127.0.0.1, which is pinging yourself. Kind of a check to make sure your network card's up and running and configured right. Okay, default gateway. So there's a 254 as an example. Mine is 192.168. Oh yeah, I'm the 140. And so there's my default gateway, same network, but it's .1. So I could ping 192.168.1.1, and I'm pinging the router, the wireless router that's there, and it says it replies, and it tells me how fast it replied and all that kind of stuff, and that's fine. Okay, again, more ping testing. So it's going to send a ping, goes to the switch, goes to the router. So now we're on a different network somewhere else. Goes off this other router interface to this other network. There's its switch that everything's plugged into, hits this PC, and the PC is going to say, yep, I'm here, sends that back to its switch, has to go to another network, so the router has to get involved to get it from this network back to this network. It's going to drop it to the switch, and the switch says, okay, here you go. You got your reply, and you would get something that looks like this content on the reply. And that would imply a healthy path to this other device. Okay, now traceroute. This is different. A ping says just I want to get back from one device to another and then come back again. Traceroute lets you figure out, well, what if you want to know information about these intermediate devices? Traceroute lets you do that. I'm finding traceroute basically doesn't work anymore because, again, there's too much of this stuff where they're turning off the responses in the devices. And so it can still have some value. When we do our exercises, we'll learn about it, but not reliable, it seems, as much anymore. But it's going to show the idea. Let's do a trace route. So it says I'm going to hit this switch, and then I'm going to go to this router, and it's going to come back and say, okay, I got this far, and we'll show a demonstration in a second. And then it goes out and says, okay, so I got that far, and I've got that input that I made it to this router. Now it gets to this router. And then I wait, and then it comes back. And all this is one exercise, one command, by the way. It shows me that, and it shows me that, and I see, okay, I made it to this router, and then I get to this router. Now it goes and does it again in this exercise, and it's kind of like, it's sort of like having packets run suicides. I mean, run to the free throw line and back, and the half court and back, and the other free throw line and back. So you're basically having your packets run suicides. And then it comes back that we made it to this third router. Then we're going to probably get to the switch. Or no, it might get past the switch and go all the way to the host. Yeah, it goes all the way to the host, so it's only a router-based exercise. So there it is, and it gets back, and that'll be the last hop, or the last iteration, and back again. And then I know the whole path that it took to get to that. So now let's see. I'm going to do IP config just to look at my machine for something, and I'm going to go to, there's some IPv6 I've got. Not a specific thing I want to look for. Okay, hold on. All right. Wireless LAN adapter Wi-Fi. Okay. Oh, it's using that for the DNS. Well, all right, fine. Let's try something else. So if I do a trace route, that command to, and you can do names, and it's tracing the route. So now it's doing that same thing we just saw. And it goes to Columbia and this number. That's our network here. So that's the first router hop. So that would be equivalent to the first hop to this router and then back, because that's the first. All right, now it found another router, a 192.168.4.34. I guess that's maybe the plant board, something like that. It'd be just a guess. 192.168.3.253. Now I have the vaguest idea. Now we're into Windstream. So the plant board, their upstream network provider, I think they've got two, and I think Windstream is one. And I think they also use AT&T or MCI. I think they use two. You know, best practice to have more than one carrier available for failover. And now we're seeing these various routes. So we went through 3 Windstream routers. So probably a plant board here, maybe here too. Then Windstream devices. Now we're probably getting a little closer to whatever particular Google server I heard, because this one, Google itself is probably on many servers with many IPs, or at least this is an IP that's like the front one for all the Google servers. And then it's going to start dropping into Google's ISP side. And then in here, I would suspect Google probably is dropping the packets. So it saw a router here, but that router is not configured to reply. And then at some point, we'll get to this IP address, the 105, as the last hop. And this will go to a maximum of 30. But having gotten the Windstream, I would think that we wouldn't really need that many more. I think you get to Windstream, and then at some random Google facility and whatever ISP that was using, and then maybe a couple of routers at Google, and then you'd be done. But we're trying to, and it might be doing 3 timeouts for each router hop. So this might actually be just 2 router hops that are 2 routing interfaces that are telling us to go away. So we can at least see we got 1, and then a second, a third, a fourth, a fifth, a sixth, a seventh, an eighth, a ninth. So we get through, you know, if you don't count the stuff here on my network, 10 routers, and then probably 1, 2, and at least maybe 3 that are not responding further. This is probably going to go on all the way through 30 and not time out. So we're going to do a Control-C, and we're going to stop it. But you can see the idea that that one command of a trace route to whatever the thing is. And you could do a trace route to this number instead, which is probably more common with some of the Cisco type stuff that we'll be doing. You get a trace route, then that number, and it should trace the same or to some degree similar path going to that host. All right, packet traces, verifying addressing. Packet tracer, we'll wait for another time. Network connectivity with ping and trace route. So you just saw one example. You can set this up in the packet packet tracer utility. When we get into that, we'll use that for troubleshooting. I've actually done a little bit of the lab work I've done so far, and works very well. Mapping the internet. That sounds daunting. And then we're talking about troubleshooting. So this will probably get into, they'll probably have you ping something and trace route something, and maybe it's pre-configured to have a problem somewhere, figure out which device has the problem, and then change it around. Okay, class activity, the internet, everything. So now we're going to back to the personal side of all this stuff. Totally optional exercise. And I think skills integration, that's always the last thing. So then you've got another skills challenge on doing some of the stuff. We'll get into doing some lab stuff, not at the moment, but we'll get through our first competitive round, and then we'll start talking about working more on Cisco and labbing up some things for those purposes. Okay, so here's the conclusion, IP addressing chapter 7. So, and this will get into subnetting in more detail, maybe not too much though. So look for that in our next video, and hope this is helpful, and we will see you next time.